Let's calculate the self-induction of a toroidal coil. Now, first we'll look at it overhead. So we have, seen from overhead, our wires are coming out of the plane of the figure, going over the top of the torus, and going into the plane of the figure. And these wires are doing this all the way around. I'm not going to draw them all, but to just give you the idea of it, coming out of the plane of the figure, going over the top, and going into the plane of the figure. This is the top view. And let's say that there are n turns. And what we'd like to do is calculate the self-induction. Now, the torus that we're going to look at, the toroidal coil, from a side view, is going to have a rectangular cross-section. So we can just imagine it like that. And this is a cut on the side, and our current goes up one side, goes over the top, comes down the other side, and comes back. And let's say that this is a height h, and from the center, this distance is a, and this distance here is b. So there's two ways to calculate the self-induction. We could calculate it either as the flux total through our object divided by the current in the coil, or we could write it as 1/2, well, we could write this as the stored energy times 2 divided by I squared. And we'll try both approaches. Both approaches will require us to calculate the B field. And when we look at this configuration, we know that this is one of our Amperian problems. And so let's first draw an Amperian loop. And we'll do it like this. I'll choose my Amperian loop, radius r. And what I'm looking at here is I want to know how much current is going to cut through the plane of this loop. And from this diagram, every single wire is coming out of the plane of the figure here. And so the total current that's cutting through the plane of the loop is n turns times the current in the wire. So if we label this, let's call it little r for a variable. Our Amperian law calculation, B dot ds equals mu naught I enclosed. And we have B times 2 pi r equals mu naught capital N times I, because there's n turns. And so we see the B field is non-uniform. So even though you might say that a toroidal coil is like a solenoid connected to itself, the B field here is very different than the field inside a solenoid, which is uniform. And now, how do we calculate the flux? Well, in this picture, we'll start with this calculation first, flux over I. This is one turn. And if the current is going like this, you can see that we have a field, B, which is looking like that. It's going out of the plane of the figure. And that's where there's flux in one turn. Now, I want to enlarge our definition of flux in one turn is the integral of B dot n hat dA. And so I'll make a picture of our one turn like this with our B field as such and a height h. Now, this is an area integral, but our B field is non-uniform. So if this is the center line, what I want to do is calculate an area element. Well, I'm going to calculate n hat right-hand rule out. And so the dot product will be positive. But as an area element, I'm going to pick a thin element like that. I'm going to call this dr prime. And it's a distance r prime from the center of the torus. And my integration variable is going to be r prime. And along this thin rectangular strip, the B field can be treated as constant. And so our integral now is the integral from r prime. And what are we integrating r prime from? A to B. We have r prime goes from A, r prime to little b. This is simply now B times our area. And what is that area? Well, the dA here is the height times dr prime. So we get h times dr prime. And now we can calculate that because the B field is, we'll take all the constants out first, mu naught I over 2 pi times h. And we're just integrating dr prime over r prime. I'll just write from A to B. And so we get mu naught n I h over 2 pi natural log of B over A. And if we want to calculate the self-inductance, we have to be a little bit careful because this is the flux only through one turn. And if you look at our solenoid, our toroidal coil, there are n total turns. And so the total flux, phi total over I, is equal to the number of turns times the flux in one turn over I. And that's precisely what we calculated, the flux in one turn. Notice the I will cancel in this calculation, and we get mu naught n squared h natural log B over A divided by 2 pi. And that's the self-induction of this toroidal coil. Now, again, it's always good to understand where the n squared comes from. One of the n's comes from the magnetic field because we have n turns of current that are cutting through this surface. And the other n comes from the fact that we have to calculate the flux through every single turn. The total flux is n times the flux in one turn. And that's the self-induction of a toroidal coil. Next, we'll do it by the energy approach.